Welcome back to class. Last week we ended up talking a bit about NASA's DART mission, which stands for Double Asteroid Redirection Test. And this was kind of in response to, we talked earlier about a meteor that exploded over the city of Chelyabinsk in Russia in 2013, and it's caused quite a bit of damage. So the thought here was that we're going to develop this DART project to be able to try to anticipate or deflect or alter trajectories of these objects before they get hit the Earth. And so NASA started to do this to try to learn how to deflect the threat. It was a $330 mission, basically, to send a spacecraft out to deflect an asteroid that's roughly 525 feet in diameter, named Dimorphos. And that's in orbit around a larger asteroid named Didymos. So that was launched on February 24th, 2021, and then it impacted Dimorphos on September 26th of 2022. And so I showed a video that kind of showed this again. So again, to kind of get back into what we talked about last week. This was the end of class last week. I'm just going to run this video again so you can see it. So this animation now will show this spacecraft impacting Dimorphos here. And then Didymos is the larger asteroid on the right. So again, this is an animation. And then after you see this impacting this asteroid, you'll see a further out view here showing its current orbital path of this asteroid Dimorphos, and then the expected new orbit that would have happened after this impact. So let's go ahead and run this real quick here. Original orbital path of Dimorphos. Spacecraft comes along, it checks a camera to view or film this event as happening, and of course the impact occurs. And now you see the expected new orbit that would have occurred from this impact.
Were they trying to change the orbit?
Yeah. What they're trying to do basically is deflect a potential threat to the Earth. Because these things, a lot of asteroids, as we'll talk about a little bit later today, are in what's called the asteroid belt. But a lot of them are kind of comet-like, where they actually have parabolic orbits. And they'll come back and they'll actually come pretty close to the Earth. So this particular asteroid that's called Dimorphos was expected to possibly come within about 800 miles of the Earth in about 150 years from now. So this, what they thought would be an ideal test to go out and test this DART mission, basically, to be able to deflect it, to be able to hit it, change its orbit, to change it to a different orbital path. So this one doesn't really have a whole lot of threat against the Earth, so to speak, and it's 150 years from now. But they thought it was an ideal one to test this theory on, this DART system on. So as we now watch this next video here, this is the actual video showing the spacecraft itself, a camera on the spacecraft itself as it approaches Dimorphos, and then it shows it impacting it, and you'll be able to hear. And I talked through this last week, so I apologize. I'll let you be able to hear what they're saying as this happens. I'll try not to say anything as this animation runs here. So let's go ahead and let this go.
A continent on Earth.
Yeah. All right. 2 minutes out.
Does not look like one single rock to me.
Oh, boy, we're getting close.
14,000 miles per hour, Roy.
14,000 miles per hour. And remember, 45 minutes ago, 55 minutes ago, we couldn't even resolve this object in space. And now you can see us zeroing in right on target.
And we're now dropping the clock, and we'll go by loss of signal to confirm impact.
Right. Yes. Imagine we'll get that loss of signal and then we'll hear from Lena Adams again, letting us know that
I
we've
feel like
been
we'll know. I feel
successful.
like that'll be a crystal clear signal.
I think so. I think we're starting to see more resolution. In fact, look at that. Didymos has even gone out of the view. We're now just seeing Dimorphos.
This is remarkable stuff.
Oh my goodness, look at that.
Looks like control system settling down, angular rates look really good. I think we're going to get the investigation team some good pictures.
Wow.
No, come on, we can do better than that.
Starting to see those individual boulders there. You can see shadows of the various rocks on the surface.
Impact. It's amazing, guys. Oh my goodness, look at that. Unbelievable.
Yeah. Looks to me like we're headed straight in. Oh, wow.
Yeah. Oh my goodness. Eight,
Yeah.
7,
Oh,
6,
wow.
5, 4, 3, 2, 1.
Oh, wow. Visual confirmation. All right. We got it? Rating? And we have it.
Okay, so here, obviously it gets closer and closer. They're expecting this to be a solid rock. They're not expecting this to be a clump of rocks, which is what we've been talking about. These asteroids were predicted by hydroplate theory to actually be a conglomerate or a cluster of a lot of boulders that were held together by ice and low amounts of gravity. So this is important to understand this, because as we go through this, you'll see the problem that occurs from this. So NASA's website features something called APOD, APOD, and that stands for the Astronomy Picture of the Day. So it's abbreviated as APOD for short. So the purpose of APOD is that each day a different image or photograph is featured along with a brief explanation of the picture, or in this case, a short video, which is written by a professional astronomer. So here the video we're going to show you here is of the impact as shot by the camera, the Leica camera, which was released from the spacecraft that impacted the asteroid. So this camera was ejected about 15 days before it impacted Dimorphos, and its trajectory essentially was parallel to that of the spacecraft that actually impacted Dimorphos. So a few minutes after the impact, it flew past Didymos and recorded the aftermath of this event. So the video that you'll see here is actually a time-lapse video. It's the best I could find, but it's the one that's on the NASA website. And this video actually is about 250 seconds of time, which is just over 4 minutes, but it's been condensed down to only about 3 seconds. So you have to kind of really watch this carefully. So it goes by pretty fast. So I'm going to play this. It's kind of grainy and it's a little hard to follow it, but I'll probably end up playing the video a couple times here so you can kind of get an idea. So here it goes. That's it. There it is again. So, so it's kind of hard to follow. But we now have an analysis of these recordings, and they're not what NASA expected. So as this thing impacted, it wasn't at all what NASA had thought was going to happen. The mission planners expect that this impact would produce a roughly uniform spray of fine dust and small particles, but the data now reveals that's not what happened at all. The impact actually kicked up lots of boulders, and some of them were quite large, and this impact kicked them out away from the asteroid at quite a high speed. So also surprising is that these boulders did not escape evenly in all directions from the asteroid. Instead they clustered in 2 main directions. So it is now realized that the change of the orbit to Dimorphos was negligible. So it wasn't really what they'd expected. If this was a solid rock, they would have thought that it would have been ejected differently than it was. So why might that be? So let's look into that in just a minute here, but I want to read the explanation that was written by this professional astronomer on this APOD of the day, which was the entry for July 28th of 2025. So he says, why was this collision so strange? In 2022, to develop Earth-saving technology, NASA deliberately crashed the DART spacecraft into the asteroid moonlet, which is a small moon, named Dimorphos. The hope was that this collision would alter the trajectory of Dimorphos around its parent asteroid Didymos, so that it demonstrates this, demonstrate that similar collisions could, in theory, save the Earth from being hit by other hazardous asteroids in the future. So analysis of the new results show that the effects of the collision were different than what was expected. And we're trying to understand why. So in the body of explanation, there are some of these words that are highlighted as links to other relevant pages. So if you read this on their website, some of the words are underlined and highlighted as links. And so the last word of the explanation was the word why. And it was highlighted as a link to another page. So I clicked on this word to see where it took me. And this is what it takes you to. Whoops, too far. That's the image you get when you click Y. I kid you not, this is what you are taken to when you click the word Y. So I guess astronomers, yeah, at least some of them must have a sense of humor, right? At any rate, I got a good laugh out of this, and obviously they were quite puzzled by this. Perhaps this rather nice-looking dog also had a chance to look at this data as well. And by the expression on his face here and the tilted head posture, which usually indicates a level of curiosity and concentration in a dog, he tries to process this information, I'm guessing. And I guess he's puzzled too by the unexpected results from this collision. So now I want to show you this. This is a still frame. Again, it's a little on the grainy side. Hope you can kind of see some of this here. This is a still frame from that short video we just shot that was shot by this camera just after the impact of the spacecraft with Dimorphos. So you can see what happened. So you see the unimpacted Didymos up here. So this is the larger asteroid, and Dimorphos is the one that orbits around Didymos, and that's what was struck here, was Dimorphos. So that was struck by the spacecraft. So what happened is it resulted in a debris field. You can kind of see it looks like a spider web kind of spread out in a couple of different directions from this asteroid. So we see it as it's spreading outward. So here's a closer up view of what you're seeing here. This is a zoomed in view. And Dimorphos is seen as this bright spot here on the bottom left of the screen. And up on the upper right side of the screen, we see what they called or circled as called the south cluster. And then on the bottom left here, we see what is called the northeast cluster. So we see these two clusters that are kind of spread out in different directions. And if you look really closely, it's kind of, again, hard to see here, but can you see all the little dots here on the screen? Those are all boulders, basically. And there were so many of them that they started to number and highlight some of them. So the yellow circles here are where they've started to actually number individual boulders. So I think they're going to try to track these boulders and see where they're going. So there's 16 boulders here that were tracked through the sequence. And you can make out quite a few more, especially in this upper right circle. So this thing hits and these things spread out in a number of different directions.
So at the beginning of the video, you hear that one woman say, "It looks like there's a bunch of rocks."
Yeah, exactly.
Individual rocks.
Right.
Did they tell her to shut up? Because especially when it comes in just before impact, it looks like a pile of gravel. You
Yeah.
know?
Yeah. And that's exactly what's predicted by
It's
Hydroplate
like,
Theory. Remember we talked
why
about
isn't
that?
They're not talking about that. It's
No,
like-
they're not. So they expected this to be a solid rock. Okay, and as we go through this, you'll see, I mean, it's pretty interesting here. This is not at all what they expected. This isn't what they expected. But this
One
would
more
be what
question.
would have been expected by hydroplate
I
theory.
got one more question. Was the animation of the impact, was it to scale?
Probably. I'm not positive of that question, but I mean, it
So
was a
it's
fairly
close to
small
scale. It was
spacecraft.
really
that-
small
yeah,
compared to the rock, right?
compared to the rock,
Okay.
yeah, what hit it.
All right, 'cause
So
I
it
just
was
wanted to
pretty
feel
small.
for
But
how it happened.
it was supposed to be just enough of a nudge to change its trajectory, to change its orbital path. But it turns out it really didn't have much of an effect at all because of it being a pile of rocks loosely held together by ice and very weak amounts of gravity. And this is significant for a reason we'll get to in just a minute here. So on NASA's webpage, speaking of the expanding plume of debris from DART's impact, they reported this. What happens if you crash a spaceship into an asteroid? In the case of NASA's DART spaceship and the small asteroid Dimorphos, as happened last week, you get quite a plume. So plume means to spread out of debris here. The goal of the planned impact was planetary protection, to show that the path of an asteroid can be slightly altered so that, if done right, a big space rock will miss the Earth. And notice they call it a rock here, because they're expecting this to be a solid rock. The high brightness of the plume, though, was unexpected by many. Right? They didn't expect this. And what it means remains a topic of research. Unexpected, of course, is that they had an incorrect beginning assumption regarding the composition of this asteroid. So they go on to say one possibility is that the 170-meter wide Dimorphos is primarily a rubble pile asteroid. And the collision dispersed some of the rubble in the pile. Okay, so remember we talked earlier about hydroplate theory and how these things would have formed as they got ejected out into outer space by the fountains of the great deep, and all heading in the same direction and the same trajectories would have allowed them to coalesce together to make, with water, and which would have become ice out in space because it got cold, would have now loosely held all this together as a rock pile, exactly as would have been expected by hydroplate theory. So they're finding now, hey, this could be a rubble pile. This isn't what we would have expected. So the featured time-lapse video was taken from the Les Makes Observatory on France's Réunion Island, which is off the south coast of Africa. So they also filmed it from there as well. And this was also, one of the many observatories from the Earth that saw this impact. So why would this be? Why would this be like this plume that would have been ejected out from this loose pile of rocks? So why would such a plume have formed? If it were a solid rock, it wouldn't have created anything like what we saw. However, if it's a loosely held together rock pile, held together by low gravity and ice, this is what would have happened according to the principles of physics. So a simple example of what occurred can be illustrated by what's called a Newton's cradle. So you probably have seen these before, right? Newton's cradle is a device that made it onto the desks of a lot of executives. As a toy, it's kind of a novelty item. They don't have a work-related function, of course. They're just intended to be a decoration on somebody's desk. But it's a classic example of physics here. It actually demonstrates the principle of physics and by the principles of conservation of momentum and the conservation of energy with these suspended swinging spheres. So one sphere at one end is lifted and then released. And it strikes the stationary spheres. In this case, you've got 5. So the one on the right here is lifted and it strikes the other 4. What does that cause it to have happen? Well, the ball on the other side now bounces away. Okay? So it demonstrates this physical, the physics of the conservation of energy here. And of course, the ball that goes off to the left comes back and strikes it again, causes the other ball to go back out again. And eventually it'll slow down, but this is exactly what demonstrates this. It's just a great way to demonstrate this. So something similar actually happens during the break in a billiards game, you know, when you're playing pool. So you've got the cue ball that strikes a rack of balls that are all touching together. This cue ball would strike the head ball, the first ball, and then the energy is transferred from one ball to the other, and allowing, you know, the other balls to scatter out. So the other balls are kind of kicked away from the original triangular formulation of balls. So from this, can you guess why this asteroid produced this plume of debris like it did, and it was not what NASA expected from this mission? This is basically when this thing impacted, it transferred energy through the asteroid. It's not a solid rock, and it's a cluster of rocks and boulders held loosely in place. And so it's kind of like what happens here with this Newton's cradle. It hits one side, and then it shoots out other directions based on, you know, rocks inside this asteroid, you know, basically doing the same thing. And eventually on a couple sides of this asteroid, it kicks this debris out into space, out beyond the asteroid. So an explanation of this actually was predicted in an email correspondence that took place just after the impact occurred. And I want to read this email to you because this is really telling here. So the very next day after the impact, which happened on September 27th, now this is before any of the video was released. This was before anybody knew outside of NASA what actually happened when this asteroid hit. Kevin Lea, now he's one of the leading advocates for hydroplate theory. He sent an email to NASA with his guess on what the DART impact did to Dimorphos before the Leica Cube camera video images were made public. So this is interesting here because being an advocate of hydroplate theory, he anticipated what these asteroids would have been made of, and so he's going to predict what would have happened when this impact happened. So Kevin is a pastor. He started a church in Port Orchard, Washington in 1993, and he was raised in an unbelieving home, but he came to faith as a young sailor in the U.S. Nuclear Navy, and he immediately fell in love with studying the Bible. He embraced Scripture as God's true revelation and source of all that we need to live in harmony with our Creator, and thus felt it was his calling from God to spread the gospel as far as he could. So he also had a background in the Navy as a nuclear engineer. So he worked as a nuclear engineering technician for about 13 years, and so he has quite an extensive scientific background, along with being a faithful Christian. So this is a great combination here. So he's somebody who understands physics, he understands science. And he's also a fervent apologist for a literal 6-day creation and a global flood, and draws on his technical expertise in science to combat the lies of evolution and the associated false interpretations of scientific evidence that we see. And unfortunately, sometimes we see in some of the other creation ministries that are out there, like Answers in Genesis, Creation Ministries International, some that oppose hydroplate theory. But this email is really incredible and shows just how powerful the predictive power of hydroplate theory could be. And if NASA had read hydroplate theory and knew about it before they did this, they might not have done this. And this is really, really striking here. So here we see it's just one of the many observations of many features from our own Earth and out in outer space that are difficult to explain by other theories, such as naturalism or evolution, which is really unguided chance, but they're actually easy to explain via hydroplate theory. And this is one of the reasons, among many, that I'm such an advocate of hydroplate theory. And there's actually a bit of a joke that kind of circulates with those who are advocates of hydroplate theory. So we joke about it a bit when we say that all scientists actually work for Dr. Brown, Dr. Walt Brown, who's the originator of hydroplate theory. They just don't know it. So they find these things out there, and it matches exactly what hydroplate theory advocates or would be expected. And so they're actually kind of working to a certain extent for Dr. Brown. So this email reads, "Hi all, since DART confirmed what all hydroplate theory advocates suspected would be the case, i.e. that Dimorphos was a rock pile, and notice the camera got closer and closer in the video, you saw it was clear that it was made up of many smaller rocks. It was a pile of rocks. I thought I should take a stab at predicting what the Leica Cube cameras will show when the pictures are released." Again, keep in mind this is before any of this video is released that shows these rocks expanding away from this asteroid. His email went on to say this, "My guess, the impact of DART is similar to that of a cue ball hitting pool balls on a break, except that instead of the cue ball hitting 15 balls in a plane that are arranged in the shape of a triangle, DART is hitting millions of rocks of various shapes and sizes and dust throughout, all combined in a somewhat spherical shape." He continues on, he says, "As such, one would expect that the energy of the DART impact, which ends up being about 11.2 billion joules of energy," so this again comes from a 14,000 mile per hour impact from this spacecraft hitting this asteroid, is equivalent to about 2.7 tons of TNT. So we talked about TNT a week or two ago. And this will cause energy to travel in thousands of ways through Dimorphos, this asteroid. And it would then transfer from rock to rock in the immediate area, which would then transfer some of the energy to the rock next to them, much like we saw with the Newton's Cradle, and then to the next rock next to those, et cetera, until the energy of each of these thousands of directions has created enough acceleration of enough mass to bring all motion to a stop in that direction. This is basically the same properties that happens when you strike a set of billiard balls with the cue ball during a break. The energy of the cue ball hitting this head ball, transfer the energy to the balls next to the head ball, and the next ball, and then it start to scatter in all directions. So this is precisely what he's predicting in this email. Again, he hasn't seen this video yet. NASA hasn't released this information yet. He said, "I would suspect that this would result in Dimorphos having some of its surface rocks at all places around the sphere of Dimorphos being accelerated away from the surface, some with enough energy to escape Dimorphos." In other words, escape the orbit around Dimorphos. So Brian Nichol is another strong advocate of hydroplate theory. And in fact, some of the slides I use come from Brian. But he's calculated the escape velocity for Dimorphos is about 4 inches per second. So at any further speed than that, they'll actually escape the sphere of influence around Dimorphos and Didymos. And now they would expand out into space. Therefore, any rock on the surface that receives enough energy impact to accelerate it at 4 inches per second or more in any direction other than the main direction of the asteroid body of Didymos will escape the sphere of influence of these asteroids and go into orbits around the sun all of their own. So now they're going to break away from this asteroid, and now they're going to go into orbit around the sun all by themselves. As such, Didymos will lose some of its mass, and quite possibly, despite NASA's promises that the DART mission would not create a hazard to our planet, put some of the ejected rocks into orbit paths that will someday impact Earth. If so, I suspect they will call it the swarm, the DART meteor shower. So recall earlier that we did not really expect these asteroids would actually impact the Earth in the year 2084. They would pass close to the Earth at a distance of around 800 miles. But now we see basically a field of ejected rocks that could actually impact the Earth. So their intent was to devise a way to nudge this thing out of the way of hitting the Earth, which they didn't think was going to anyway, but it was a good one to try this out on. But they've actually now created a problem, a big problem. Kevin goes on to say, "I would also expect that some of the impact site rock will be pulverized into powder and ejected, as one would expect from 2.7 tons of TNT impact energy. The pulverized rock will be ejected in an expected cone shape with velocities that will also put the debris in their own orbits around the sun." Again, this is before he sees any of this video we just showed you of the impact. "I would suspect that Earth-based telescopes will see a larger light reflection from Dimorphos at first as escaping rocks reflect light back to Earth's observers. According to the article below, they will not be releasing the pictures of the impact until tomorrow. This is my best guess ahead of time. I may be wrong about the above, but time will soon tell. But one thing for sure, the DART mission planners thought they would be hitting a solid asteroid, which was based on the Big Bang paradigm of how asteroids were formed. However, the results of the DART test were exactly as predicted by Hydroplate Theory. Again, looking back at how to assess the viability of a theory is, can you make predictions on it that come true? Well, again, this is another one of the many predictions that we see that have been validated by the Hydroplate Theory. And here is a picture of the impact as recorded by a camera here on Earth that happened on September 27th of 2022. So notice again all the material around the asteroid. This is from quite a distance away, of course. But they didn't hit a solid rock as they expected, just like Kevin had predicted. It was, again, like a pool ball hitting a set of billiard balls on the break. And this predicted amount of debris was scattered outward away from Dimorphos. So the ATLAS project actually consists of 4 telescopes. So this was viewed on this ATLAS project. So there's 4 telescopes here on Earth, 2 in Hawaii, 1 in Chile, and 1 in South Africa. It's actually on an island just off of South Africa. And they scan the whole sky several times every night looking for moving objects. So now here's a video of this impact as we see it from Earth. The video plays twice, so watch it, but you'll see this actually happen. You don't see the spacecraft, of course, it's too far away. But we're going to play again there. And as you see that, you'll see this field of debris just spreading away from this asteroid. Right? So this was taken from this observatory off of the coast of South Africa on an island called Reunion Island. And again, this is one of many Earth-based observatories that followed this impact. And the initial dot is primarily Dimorphos' larger companion, the asteroid Didymos. And most recently, the images show that Didymos and Dimorphos have developed comet-like tails. As earlier stated, the goal of ATLAS was to provide a warning system to warn the Earth of potential strikes before they actually strike the Earth. And the detection system's warning times depend on the size of the asteroid. With the larger the asteroid, the earlier it could be hopefully detected before it would actually hit Earth. ATLAS can see, it said, a small meteor of around 20 meters or about 65 feet in diameter about several days before impact. So it's not really all that much of a warning ahead of time. And about a 300 or so foot in diameter asteroid around several weeks before impact. So a 300 foot in diameter asteroid has been estimated to have approximately 10 times the destructive force of the recent Tonga volcanic eruption, which you may have heard about. It's on YouTube, and I can provide a link to this if you want to see it, but this is from a volcano that exploded at the bottom of the Pacific Ocean. And so this impact, if we had a 300 or so foot wide asteroid actually strike the Earth, it would be 10 times the destructive force of this Tonga volcanic eruption. So let me show you this volcanic eruption to give you a sense of how powerful this eruption was. This is out in the middle of the Pacific Ocean. This eruption occurred on the ocean floor near the island of Tonga, which is an island country made up of about 171 islands, and 45 of these islands are inhabited. And these islands are close to Fiji and around 2,170 miles or so due east of Australia. So this Tonga volcanic eruption occurred on December of 2021 when this submarine volcano erupted in the southern Pacific on the ocean floor. And this was described by scientists as a mega hammer that generated the largest atmospheric explosion ever recorded by modern instrumentation. So it produced volcanic tsunamis that were felt in many locations, as far away as New Zealand, Japan, Chile, Peru, and even the United States. And tsunami waves produced by this volcano were tremendous. So at least 4 people were killed, and some were injured, and some remain possibly missing in Tonga from the tsunami waves that were up to 66 feet high. So the interesting thing here is that we'll find out later on when we get further into the class why there are volcanoes on the bottom of the Pacific Ocean. There's about 40,000 volcanoes at the bottom of the Pacific Ocean. How did that get there? We'll get into that later. But this volcanic eruption was so tremendous, NASA determined the eruption was hundreds of times more powerful than Little Boy. So the Little Boy was the code name for the atomic bomb that was dropped on Hiroshima, Japan, in August of 1945 to force the surrender of World War II. So the eruption of Tonga was the largest explosion ever recorded in the atmosphere by modern instrumentation, far larger than any 20th century volcanic event or nuclear bomb test. Now, if an asteroid of around 300 feet in diameter would strike the Earth, it would be 10 times more destructive as this. Obviously, this is a very serious issue. When we go further on to the class, again, we'll talk about all these volcanoes and why there's volcanoes at the bottom of the ocean. This, again, is another effect of the flood. Do we have the second bell yet? I don't think we did. Okay, we got a couple more minutes. So, again, this volcano and other volcanoes can be directly linked back to the flood. And as we see now, the flood continues to do damage. I mean, thousands of years after it occurred. So we're seeing now asteroids come back and strike the Earth, causing damage. We see tsunamis, tidal waves, volcanoes. These are all a result of the flood, using well-known cause and effect relationships, and all links back to the fountains of the Great Deep bursting forth. This is how significant this is. This is why this is, I think, is an important thing to look into, is that we have an answer for why all these natural disasters occur. It's really, really incredible. So, one more quick slide here. Here's a photo of the Atlas project following the DART impact that gave Dimorphos a debris tail thousands of miles long. So on October 11th of 2022, NASA declared the DART project a success, confirming that it shortened the Dimorphos orbital period around Didymos by about 32 minutes. But was that a success? So there's just a little bit of a change in its orbit. So on March 27th of 2023, Kevin Lea sent up a follow-up email to Dr. Brownlee, who works for NASA. And in the email, he writes, questions related to DART. There's been very little news about the DART mission since impact. I'm wondering about the following. If the success was expected to be a change in Dimorphos' total orbital period by 73 seconds, why was it 32 minutes instead? I know we're out of time. We're going to have to stop there. I'm sorry. You know, I wish we'd just keep on going. But anyway, we'll get into this a little bit more next week, but they did not expect this. But they finally have admitted what they've done actually is created something that could be a big, major problem by doing this. And again, 150 years or so from now, the world's going to have to deal with this. So anyway, thank you. See you next week.